Hi, everyone. Hi, everyone. Welcome to our Berman Institute of Bioethics biweekly seminar series. Joe Ali, I'm the chair of the seminar committee. Delighted to be joined by my colleague Khadija Ferryman from the Berman Institute, who'll be introducing our speaker today. He's also with us. And let me just begin by reminding folks, and for those who are new, that we'll have about 40 to 45 minutes for our speaker to present, and then we'll have an opportunity for some discussion and question and answer period. If you do have any comments or questions, please feel free to drop them in the chat or the Q&A module at the bottom of your screen. We'll take them in order of appearance. We'll do our best to get to all of the questions if we're able to within the time frame, but if not, apologies in advance. And I think with that, that's about it. I'm handing it over to you, Khadija, to introduce our speaker. Thank you very much.
Great, thanks for that, Joe. Hi, everyone. I am so excited and honored to introduce my colleague and co-author and friend, Dr. Marzyeh Ghassemi, for our seminar today. And Dr. Marzyeh Ghassemi is an assistant professor at MIT in the electrical engineering and computer sciences and the Institute for Medical Engineering and Science, and is also a Vector Institute faculty member holding a Canadian AI chair and Canada Research Chair. She holds a Herman L.F. von Helmholtz Career Development Professorship and was also named one of MIT Tech Review's 35 Innovators Under 35. And previously, before MIT, she was a visiting researcher with Alphabet's Verily and an assistant professor at the University of Toronto. And prior to completing her PhD in computer science at MIT, she received an MSc degree in biomedical engineering from Oxford University as a Marshall Scholar and BS degrees in computer science and electrical engineering as a Goldwater Scholar at New Mexico State University. Professor Ghassemi currently serves as NeurIP's workshop co-chair and general chair for the ACM Conference on Health, Inference, and Learning, and also has a well-established academic track record across computer science and clinical venues, including NeurIPS, KDD, and JAMIA, Nature Medicine, many other journals that you can look at, and her work has also been featured not only in academic literature, scholarly literature, but also in the popular press, such as the MIT News, NVIDIA, and the Huffington Post. And she has many other interesting works and accolades that you can see on her website if you Google her. But I will leave it there with that short intro and hand it over to you, Marzyeh. We're so excited for your talk, and thank you so much for spending the afternoon with us today.
Thank you, Khadija. All right, I'm going to, I just shared with everybody previously that I actually dislike Zoom and don't think I'm particularly competent at using it, despite an entire pandemic worth of experience, one would hope. All right, so I'm going to talk to you today about my general thoughts with some very specific research examples on how AI could be the fairest of them all or not. And the focus that I'm going to take you on in this talk is looking at privacy, data, and how those two facets of what we do are actually related to fairness in machine learning and health. So to start, I want to let everybody know that if you haven't been reading in this space for a while, or this is not your normal academic community, we are in a place in machine learning for health where we know that state-of-the-art methods can perform at or above humans at tasks across the human lifespan. So that's not a question anymore. If you can define a good task, then probably I can train a machine learning algorithm to do that task in the way that data shows me humans have been able to do it. So it's dependent on data and task definitions, but many, many wonderful groups all across the world actually define these tasks and then train models to do things at these different levels. And so each and every single one of those lines in that table essentially does machine learning for health in this way. They get data, but you need data to train machine learning models. And you can get data from practice. So going into a hospital and taking all of their records, that means you're watching how doctors practice, or you could get it from knowledge, right? So I'm going to read, I'm going to give my model textbooks and randomized controlled trial information, PubMed articles, and you'll learn from those. And then you can train machine learning models with machine learning statistics. And then you predict something, you predict clinical events or treatments. And so it just, like, let's look at that first part, because, now as a community, we're all kind of, gasping and looking at that first part collectively. Because when we learn from knowledge, let's say we take the gold standard in medicine, randomized controlled trials, right? Well, randomized controlled trials are actually really rare. So only 10 to 20% of the treatments that we use in hospitals are based on RCTs. And that's not because, humans are evil and want to hurt other humans. It's because these are really hard to do. They're very expensive. They take time. When you do them, because the way that you run a randomized controlled trial, in case you've been paying attention throughout this pandemic, is you select a population that's very homogeneous so that you can examine the effect of a very specific intervention, right? And so you're controlling for so much and just varying one thing, this intervention. And so what that means is often you select a target population for your randomized controlled trial that is completely non-representative of the actual disease complexity in real people. So only 6% of asthmatics would have been eligible for their own treatment RCT. The other 94% that are currently being treated with these guidelines would have been ineligible. And finally, even once you have treatments that you use, often we discover later they're wrong, right? And so if you look at these top medical journals like Lancet, New England Journal, JAMA, in the last 10 years, over 10% of them, so that's over 3,000 articles, will come out that are these medical reversals, which means we discover that something that we do in the clinical community is actually really bad for patients and we should stop doing it, right? So an example is giving estrogen to postmenopausal women. All right, well, it sounds like there are problems when you train machine learning models from knowledge, right? It might learn things that we don't want it to learn. What about practice? Why can't we just do that? Well, when you're observing in a hospital, you're observing clinical devices that don't actually always function equally. What I mean by that is famously, actually, during the pandemic, pulse oximeters don't capture oxygenation levels for darker skin exactly when you would want them to at low oxygen saturation. Slightly problematic. You also have clinical interventions you're observing that are often designed for majorities. And so there was a lovely paper that came out this year, or actually last year, that showed that risk scores that include race, and these are real clinical risk scores across several different fields in medicine. They use race, and that over or underestimates minority risk assessments. And so, you'll have this clinical score that's calculated, but if you were to put that in your model, it would actually give you a poor risk adjustment for minorities. And finally, when you're trying to define your outcome, right, a specific diagnosis, for example, often those are defined on these really, again, homogeneous populations. And so we have a real rarity of darker skin in dermatology that can lead to underdiagnosis because we don't know how to define specific conditions in darker skin. Or female patients disproportionately have low heart attack survival, but only when male doctors treat them because we're not paying attention to the things that these patients are saying in the way that it presents in these patients. So these are some problems, right, with learning from practice. And so maybe a final thing for everybody to realize, right? So initially I showed you the fancy table of all the things we can do. And now I've poked a couple of holes in how that fancy table gets made. We always collect data in machine learning in health on people who are sick. That makes sense, right? When do you have data on people? You have data on them when they're sick, okay? And then remember that table I showed you, we're predicting when bad events or outcomes like getting worsening sickness happens. And machine learning researchers, just to be clear, have really engaged in this field. This is not like one lab does it, occasionally there's a paper. In the past 10 years, there's been an entire community. It's at a point where there are not just focus areas in mainstream machine learning conferences that you can submit a health paper for. There are whole separate conferences now that focus on machine learning and health. And models are not just an academic exercise anymore. They're now regulated advice givers. So the FDA, for example, has cleared several machine learning algorithms. This is just in the first 6 months of 2021. I took this snapshot a couple months ago. So this is something that has real consequences, right? These are models that are being trained and being approved in some way to give advice to clinicians. And so the thing that I want you to now think about is bad events in sick people. What is that technically? That's anomaly detection in anomalous data. What I mean by that is this would not be like taking photographs of normal people walking around and then asking you to classify whether those are humans or not, right? This would be like saying, I'm only ever going to show you photographs of humans in Halloween costumes. And then I'm going to ask you whether this person, and always in a Halloween costume, you've never seen humans that are not in Halloween costumes, are doing a dab or some action, right? And so you're asking me to detect an anomaly and data that's already anomalous, a worse event in people who are already sick. And this is really challenging for our entire field because we've been looking where the light is shining, which is bad events in really sick people. And so we have very little idea of what it means for a diverse population to actually be healthy in the first place, which is ideally where you'd like to start from in a lot of these machine learning tasks. And so a lot of what I try to think about in my research is what exactly are we learning in healthcare when we focus on this kind of data and these kinds of problems. And so I'm going to walk you through 3 areas that my group generally focuses on to create actionable insights in human health. Those are what models are healthy, focusing on the actual development of models that work well in this space, what healthcare is healthy, how do we actually account for the fact that this data is often biased and it's part of a care system, and what behaviors are healthy, because ideally we'd like to deploy these models and we don't just want them to be academic papers, we want them to work well in practice. So on the modeling side, the example that I'm going to start with is privacy. I'm going to start with that because privacy is having a big moment right now in machine learning for health, where it's well known that anonymization itself is not robust to linkage attack. That's why when you release anonymized data sets to researchers, you release them with legal teeth, like a data usage agreement, an IRB, data usage agreement, different kinds of legal teeth to ensure that I am not going to do something bad with this data, because it's not impossible for me to re-identify. And so there's been some push in the community to try to use more technically robust definitions of privacy. And so one potential technical framework is differential privacy. And differential privacy is a framework that allows you to provide the same level of privacy protection to all individuals, regardless of their uniqueness. And so why is this important? Because linkage attacks are actually really sensitive for those who are relatively unique. Meaning if a person like Sumana is in data set A, and she's the only person of her gender, race, and age in her zip code, then those properties alone can make her uniquely identifiable to an adversary who can look at this anonymized data. And the way you can think about that is if we anonymized a data set that contained me, but I'm the only half Norwegian, half Iranian person in zip code 02140, then it's going to be very easy to identify me even with anonymized data, because I'm going to look like I stand out. There's nobody else, right? Like it must be Marzyeh. She's the only one there. And so differential privacy protects people who have those combinations of unique attributes. The way that this is done is by noising and clipping gradients during the learning process. And so if I have a neural network here and I'm training it to predict something like mortality in a hospital. One way that I might do that is I might say, you know, every year I'm going to look at the data that's in a hospital. I'm going to take all of the data from past years and I'm going to train a model with that and then use this trained model to predict mortality in a future year. So my performance at 2009 will be based on models trained on data from 2008 back. My performance in 2010 will be based on models trained on 2009 and back. And the way that we are going to inject privacy in this is through this differential privacy framework. Every time my neural network makes a prediction on mortality, right, I have a true label. I actually know if this person died. And so I can measure a loss between the parameters of my model and what I would like them to be to ideally predict this thing I'm trying to predict. And when I take a gradient to figure out which way to make my model move to make it a better model, I noise that and clip it if there's any data point, any person who's too unique, right? Because that person, if they're too unique, is going to pull my gradient around, you know, a little bit more than with other people. And that's what might make them identifiable. And so what we found is that unlike in natural language processing or in vision, when you inject differential privacy into healthcare tasks, you pay this really extreme utility trade-off. What I mean by that is models that normally perform between 0.8 and 0.9 for AUC. These are reasonable AUCs, something that you would maybe feel comfortable deploying. And these are models that we evaluated every year from 2003 all the way up to 2013. They lose their performance going down to almost no better than chance, which is here a performance of 0.5 when you inject privacy, a high level of differential privacy. And that kind of a loss is really not acceptable in a clinical prediction task setting. And what's maybe even worse is where we're seeing a loss of influence on the inside of this model performance. And so you can think about influence as the amount of pull or support or help that any training data point has on any new test data point that comes in and asks to be classified. And what we find is that by adding in even low levels of differential privacy, you flip the most helpful ethnicity, ethnicity of the training data that is helping you make a decision on this new test points from Black patients. When it's a Black test patient, the most helpful other kind of patient to classify this new Black patient is in the training data, often another Black patient. When you inject low or high levels of differential privacy, you flip that to always being a white patient. And so you're removing influence. Adding privacy is changing the most helpful group training data from Black patients to white patients for Black test patients. That's really problematic, but I want to emphasize that there's no evil trickery happening here. This is working as designed, right? Because machine learning models are built on finding and enforcing similarity. And that's really powerful. It's why machine learning can do all these really wonderful things. Like if I want to try to classify an unseen data class, right? So I want to identify shoulders and skirts. There are methods like zero-shot learning that take advantage of having seen things like arms, hands, and shirts to extend that kind of knowledge to unseen classes and say, I may not know what this class looks like, but I've seen things similar. And so it's a really powerful thing to be able to say, I'm going to find similarity, I'm going to find patterns, and I'm going to enforce it. It makes learning much more efficient. That's what humans do. However, in health, we're not talking about a noisy data point or a blurred image or garbled text. Every single one of these data points is a human. And so the problem is, what does it mean if a human is an outlier that gets clipped or noised or removed? And that brings us to this middle space of problems where models probably can't solve them alone, right? And so this is because bias is part of the clinical landscape. We're seeing that machine learning models are biased in clinical settings, not because machine learning is evil and wants to hurt people. It's because these models are doing as we do, as we've shown them that we perform in medical settings, as we've written in medical journals, rather than, what we say we do. And so if bias is part of the clinical landscape, it's an important question for us all to think about: how should machine learning interact with the clinical landscape? And so one example of this that is coming out in a month, I think it's coming out soon, is a study we did where if you're in this space, this is a very popular task. Everybody does this. You take a lot of chest X-ray data, and then you try to elicit a diagnosis using a machine learning model. Okay, so in this case, we took the three large public chest X-ray data sets, so it's over 700,000 images. And we trained a convolutional neural network, specifically a dense net, but we didn't train it to do what most people do, which is predict pneumonia, effusion, pneumothorax, these normal sort of diagnoses. We trained it to predict another label that's present in the data: no finding, meaning the model says the patient is healthy. Or in this case, the model is learning when clinicians or radiologists say that the patient is healthy, okay? And then we wanted to look at the false positive rate in different subpopulations. And we're calling that model underdiagnosis. We're calling it underdiagnosis because if you have a higher false positive rate for no finding, right? Patient is healthy in one subpopulation, like female patients. If you deployed this model, it would lead to a higher rate of no treatment in patients who actually need treatment. They're really sick, but you false positively say they're fine, right? Healthy, no finding. And so what we find is that these state-of-the-art models, when you train them, actually do have significantly larger underdiagnosis rates in female patients, young patients, Black patients, and patients on Medicaid insurance. And the intersectional identities are often more underdiagnosed than aggregated groups. That means Black or Hispanic female patients are underdiagnosed by the model. These are unseen patients where we know the label of what they actually have, more than white female patients. That's problematic, but you might look at this and say, okay, it's great that you found that out. Now that you know that it's there, why can't you just audit it? Why can't you just do what we did in this model here and say, we know that there may be significant differences in model accuracy based on race, sex, or insurance type when you train machine learning models. Just audit it and try to correct it based on whatever algorithmic notion of fairness you have in this setting. Maybe in some settings, false positives are more costly than false negatives. And so I'm going to weight that differently in different populations for different prediction tasks. But I want to emphasize, this is actually really hard. How hard, you might ask? So we took a contextual language model. And so contextual language models, if you don't know, are these transformers that are trained on lots and lots of text from different sources. And they beat the human Turing test. So humans can't tell that a model is generating the text when they're asked to, for example, fill in a blank or generate a few sentences. And so you can experiment with these online. A lot of people have BERT or GPT-2, GPT-3, different kinds of models that have been pre-trained where you can ask questions and it will answer, or there are chatbots that use this now. Famously, the NHS in the UK used a chatbot made by Babylon Health to answer clinical queries for a little while. And so what we did is we took SciBERT, which is a version of BERT that's trained on PubMed, so scientific articles, right? I want to emphasize, it's trained on scientific articles, not 4chan, not Reddit, okay? And we gave it this prompt, which is a real extract from a real clinical note at Beth Israel Deaconess Medical Center Hospital. And so the prompt is, blank patient became belligerent and violent, sent to. So if I fill in the first token with Caucasian or white, the model completes the sentence, the note, the record that might go into an actual EHR if you were using a model like this to help you fill in records to autocomplete. Hospital. If I put in African, African-American, or Black, the model fills in the blank with prison. this would be really hard to catch. You have to check many examples, and you have to know what kind of social biases might be present, even in scientific articles at a level so deep that a model trained on them will replicate them in seemingly innocuous text settings. And that's because health is complex. It's a process, a socio-technical process that generates complex data. And so we need to think about the human behaviors that we're trying to elicit: better diagnosis, fairer treatment, and then design systems that can help us with that. Because non-medical factors greatly influence care. So even forget about the first two parts of my presentation, pretend we have a perfect model that's trained on perfect data. We know that even with rigorous medical knowledge, the way that you deliver care changes how well people absorb it and whether they actually want it. And so the three examples that I always find really grounding to go through in talks are, we know that physician-patient race match reduces the likelihood of in-hospital mortality by a significant level. Black doctors are more successful at getting Black male patients to agree to standard medical screening. And my personal favorite, because I once was giving a talk like this, and they said, a person in the audience said, but this is for minorities, right? There are very few minorities, and maybe they have a very specific, by definition as minority, there are very few of them, and they have a very specific experience with a system. And you can't falsely rebalance that population, right? Like you are by definition very few people. Women are not a minority, right? And yet gender concordance increases a patient's probability of heart attack survival. And the effect is driven by increased mortality when male physicians treat female patients. And the beautiful excerpt I always talk about at this point is, this is because mortality, one really interesting fact that they observe in this good paper that everybody should read, is that mortality rates decrease when male physicians either practice with more female colleagues or have treated more female patients in the past. And what I read that as is, if you have treated more female patients, that means maybe you have learned that if I ignore certain words, or if I am distracted, but only with female patients, they die more, right? I have this experience. I let a female patient die on my watch. I'm going to do better. The really interesting thing for me is that mortality rates decrease when male physicians practice with more female colleagues. And the joke version of this is, when you're around women more, you want to kill us less. But the real version of this is, you can be trained. If somebody around you, in this case, a female colleague, is giving you some insight into something that you're doing incorrectly, you can fix that. And I find that incredibly hopeful, actually. And so this is a famous study that we were inspired by. So I'll go over it briefly, from long ago when there were iPods. I don't know if anybody remembers this, where they did an eBay auction looking at iPods, where researchers were only varying one thing: the color of the skin holding the hand, or the color of the skin holding the iPod. So the hand is a different color. And they found that white hands holding iPods receive 21% more offers than black hands. And so they get a lot more money for those iPods because more offers are coming in. It's the same iPod, same text, everything's the same except for the skin color. And so we thought we would try a modified version of this, where we gave advice to clinicians in an X-ray diagnosis system, right? And we told clinicians that the advice was either coming from an AI or a human. In all cases, the advice came from us, right? The only thing we varied was whether the advice was accurate or inaccurate. And so we're varying these two things, right? Whether we tell them it's from AI or a human, and whether the advice is accurate or inaccurate. Everything else is the same. We present each person with 8 cases in total, and we measure 2 things: how accurate they are at their diagnosis, and also what quality they think the advice is. So their perception of the quality of the advice, and then how well they're able to perform. We have two populations that we looked at here. We looked at experts, radiologists who do this all the time, and non-experts, IMEM doctors who see x-rays and do some of these reports, but it's not their main thing. What we found is that there is reasonable algorithmic aversion in the experts, meaning radiologists rate AI advice as significantly lower quality than human advice. It's the same advice. We just are saying that it's AI advice, and they say, oh, it's much worse when it's AI advice. That's not true for the non-experts, for the IMEM doctors. But we find similar levels of performance no matter what kind of advice it is. And if we dig a little bit deeper, so they don't trust the AI, they think it's much worse quality, but forget about what they say, let's look at what they do. What's interesting here is that experts, radiologists, they have a better diagnostic accuracy. So a little bit more than half are getting 7 out of the 8 cases correct. But some doctors here are more susceptible to the incorrect advice than others. And it's a similar ratio of people. And so here, radiology participants 60, every case that they saw with accurate advice in blue, they got right. But they got 0 cases where they were shown incorrect advice correct. And so any one of these bars that's all blue, that means that every time they saw correct, or they only got advice that was correct in the final judgment. And so that's really concerning, because all models are going to be wrong. There is no actual perfect model, right? How do we make models that when they present the wrong information, because occasionally they're going to be wrong to clinicians, how do we make models that when that happens, the clinician will be able to dismiss it and still get the case right? We don't want them to be susceptible to this sort of algorithmic incorrect advice. And so, the problem is there's no simple fixes here, right? It's not as if there's one thing we could do to address some part or many parts of this problem. There's an entire pipeline that needs to be considered in any kind of a fix we propose. And it's an ongoing process. It's going to require reasonably diverse engagement, I think. But I want to focus for a second on item 2, because I think this is where the field has started to really engage on the data collection side with saying, oh, we have a real problem, and that's affecting everything downstream. So data is hugely central to doing machine learning well, to doing medicine well. And this has been a problem in medicine, and now we have a trickle down effect where it's a problem in machine learning. For so long in medicine, we've had really homogeneous populations define what our diagnostics are, what our criteria are, how devices should work well. And now we're seeing the trickle down of that problem as machine learning models say, okay, I can use those definitions you have, and I'm going to perform really poorly in minorities, in women, in people who are excluded from those definitions. And so all data is valuable, but health data is particularly valuable. And I think a personal, platform / plug of mine is private corporations can buy de-identified data and then use it to create diagnostic models, prediction tools, but often those same places that are selling de-identified data to corporations don't want to make the data available to researchers, right? Because they're making a lot of money off of the sale of that data. And so they don't want to just give it up, right? Like they've got a gold mine, they don't want to give the gold up. But I think that it feels to me like it should be a more well-regulated public good, because this data is in large part how we will understand what kinds of models are working well in different populations. And so health in general really lags other machine learning subfields in reproducibility. So if you look at natural language processing, computer vision, or just general machine learning, the machine learning and health papers that are published in high quality conferences and journals lag in releasing code, releasing data, and leveraging multiple data sets. And that's because, again, often restrictions are placed where people think, I'm sitting on a gold mine, I won't give up my gold, right? And synthetic data, which is one of the favorite solutions that people have proposed to me as well, I can't give you this data so you can verify my results. I can give you something synthetic. Synthetic data is not a robust solution. And it's not a robust solution specifically to algorithmic bias as well. And what I mean by that is, let's say that you have a biased data set that's only 6% female. And you say, well, I can just add noise and perturbations and change my, my data set so that it's artificially balanced, it's synthetically balanced. So we found that biased data sets have really disparate impacts on minority downstream classification influence, even when the real data set was not directly used. So even when we're using a synthetic data set that is balanced for training, synthetically balanced. And so you can't just supplement or replace data sets with synthetic data. That doesn't mitigate these fairness concerns. We actually have to collect data that is more balanced and allow people to use that. And post hoc balancing, which is another popular suggestion that people, you know, these are like my revenge papers. You know, I had some person tell me at some point when I did a data or information request, well, we can just do this. And then I had students write papers dismissing those notions. So that's how these came about. So post hoc balancing, it turns out, doesn't work either. What I mean by that is, let's say that you have access to a bunch of data and you don't want to share it with other researchers for them to audit or do their own research. And so you say, I'm going to learn some sort of representation space or embedding space, and I'll release that. You can't have the original data, but you can have this representation. I'll release that. If you have bias in the data that created the embedding, even if you train at downstream time for a new classification task with balanced, completely balanced training data, you still have biased performance in the downstream task. And that's because if I learn a sphere to embed people on, and there's a big hole in one part of the sphere because I had very poor data representation, there's never going to be a way to accurately, with high fidelity, project new balanced training data onto that portion of the space. And so this is a loss that's going to be felt all the way down the pipeline. But if I don't have the original data, I can't audit it appropriately because I can't check what the distributions were. And so these issues are really just the tip of the iceberg, right? We're in a system now that has recognized there's great power in being able to use data to automate, improve, or augment practices in health. And I think that realization has thankfully shone a light on this question of what exactly do we want to automate here? We don't want to do all of this, right? Because it's not all great. And when we augment a person, how should we do that in a way that's allowing them to perform best without being susceptible to errors that the model is going to make? And these are all really difficult questions that are going to require more research. But in addition to my lab of fantastic students and collaborators, there is a really robust community that is built up around doing machine learning for health. And I think it's an exciting space to be in, because if we can address these different concerns, I think we really can have actionable insights in human health.
Great, thank you so much, Marzyeh. And of course, if you were here in person, I think you'd hear, you know, the round of applause. So virtual round of applause for you. Thank you so much. And apologies right now, there's a lawnmower outside, so it's very noisy, but hopefully you can't hear that. We do have a question in the Q&A, which we can get to, and I can also check the chat too to see if there are additional questions, but I would ask everyone just to please use the Q&A function for your questions. But I want to take kind of moderator's privilege just to ask, to start out with a question. about the slide that you presented about the radiologists and the sort of non-specialists who, and this observation of certain groups, certain kinds of, or certain physicians being subject to being susceptible to not catching the inaccurate diagnoses, right? And so I just wanted to hear more about that if you were able to. I think it was, radiologist 60, right? That was like never caught any of the inaccurate ones. Did you find any sort of characteristics about the specialists or the non-specialists that sort of, any patterns there that gave you some insight as to why these particular clinicians were so susceptible to not finding the inaccurate diagnosis?
Unfortunately not. We looked at all these different facets of who these clinicians were, right? The information that we had about them. And there's nothing that ties them together other than, their level of expertise, right? Like what their perception of their level of expertise. And so some of it, it could be a little bit of hubris, right? Like if there was a mistake, I'd catch it, right? And so I don't see a mistake, so it must be fine. But this is a very well studied phenomenon in other fields, this so-called automation bias, right? Where if the default is to play the next episode on Netflix, that tiny little nudge, that tiny removal of a barrier for my action creates this really strong automation bias, right? That's why in so many technical settings, so many companies have things automated for you. Do you just want to have this be a monthly order? Should I just schedule that for you? Would you like to up this? It'll be up, your contract will be upped by default. You have to click this to say no. And so I think that we're dealing with a very human susceptibility problem that's sort of hinging on this automation bias. And it's a similar proportion of people who are susceptible. I think the surprise for me there was I sort of thought expertise would be protective, right? I think my co-authors and I had assumed that it would be protective, but nobody's really studied this specific phenomenon in medical AI interactive settings. And so in our study, specifically looking at this kind of decision and this kind of prompt, this kind of advice, it appears to be generally true. So your expertise is not protective for susceptibility to inaccurate advice, unfortunately. We do have a study though coming out soon, which I'm very excited about, where we find that depending on how you present the advice, you can be protective. And so the specific difference that we found is you have to be descriptive rather than prescriptive, right? So here we're giving them the advice of what the diagnosis is and saying like, I think the diagnosis should be blah, right? And whether we said it was from a human or an AI, they're susceptible to it, right? They're just following it, automation bias, right? But in another study that we've done, this time in a text setting, we're finding that even if we give them incredibly biased, unethically biased models, which we intentionally bias to be unethical, if we present it in a descriptive way of not giving them exactly the action we think that they should take, but describing what we think they should do, it does not bias them. So they're not susceptible to that as much. And it's this space of research that I think we really need to start engaging with, of how do you make sure that you can give people the best advice possible, but also have a little humility. Your model will be wrong sometimes. You need to figure out how to deliver that so that when it's wrong, it doesn't destroy everything.
Great. Thank you so much for that. And let me just ask one more question, because we have until 1 o'clock. So let me just ask one more question. And I see one question in the Q&A. So I think we, with what we have now, we should have enough time. So I wanted to ask the question about the differential privacy topic that you brought up, right? And this very concerning finding that adding differential privacy, which for those of us in the audience who are interested in ethics, right, we think about privacy as this, well, I won't speak for everyone, right? right? But we clearly think about privacy as an ethical issue and something that's important to consider. And so this move of thinking about differential privacy, adding noise to your data to protect those who would be most vulnerable to being identified in a data set, you know, as you mentioned, at first blush, that seems like that would be a good thing. But as you showed us, right, there's this loss, right? There's this, you call it the kind of loss of influence that, again, affects, disproportionately impacts those who we maybe were trying to help with our, with our differential privacy intervention. So, so this is you know, again, an interesting and sort of concerning finding. And I want to sort of couple that with the later part of your talk where you mentioned private companies and how they are also getting access to data and building these models. How are private companies sort of dealing with this differential privacy issue? So, right, because it sounds like this is something that the ML research community is sort of thinking about and realizing some of these issues, but is that even something that private companies that have all this health data are even thinking about or using, or how is that playing out in the private space?
So let me say two things about that. So the first is the way to solve the differential privacy, the privacy fairness trade-off. The way to solve that is data, right? The reason that so differential privacy is working and is designed here is it's saying, well, there's only two of you. You're going to be uniquely identifiable. I have to noise this about you, right? Or clip your influence in some way, right? And so the model's not broken. It's not doing something wrong. It's working as designed. Our issue is that we have so few data points, right? And so, and that's really hard. It's not easy to collect data. Also, there's a question of if I am misperforming in a minority group because I have relatively fewer data points about that minority group, the solution is to over collect data from that minority group, but I don't really want to be surveilled. In fact, my particular minority group, it has issues with surveillance already. So I would not like to give up more data right now. That's not an easy question. That's a very hard question, right? Just in terms of like that trade-off of privacy and fairness. I was surprised, but the algorithmic fairness community, the theory community that does differential privacy and algorithmic fairness, this is a known trade-off. Like it's a known trade-off that as you turn one dial, sort of the other goes down. And I think different communities and countries fall on different sides of this line of where I'm going to land. In a private setting, there's sort of two settings where you might be thinking about this. The first is companies already use sort of, you know, famously differential privacy to protect the privacy of their end users. So autocomplete for Google, right? Like they're using differential privacy so that nothing I type is if I always type DuckDuckStone instead of DuckDuckGo, maybe I would be really freaked out if I wrote, I'm going to the duck. I was going to write pond today, but it said stone because it's learned that this is something that's kind of unique to me. So maybe that's a funny example, but if I was looking for something that was related to abortion, HIV, sensitive health issues that I don't want to be tied to myself, you would want that protected. And so the US Census uses differential privacy. Apple to protect the browsing and usage patterns of its customers uses differential privacy. And that all makes sense. There's a ton of data and it's probably not terrible if my search patterns are relatively unique. And so I get slightly worse performance in my autocomplete because I tend to search in sort of a distinctive way. The problem in health is that any trade-off in utility feels wrong, especially if it's for groups that have historically been disadvantaged in health. And so my personal position, and there are many people who disagree with me and have different opinions on this. My personal opinion on this is that until we have enough data that we can actually train differentially private models in a way that is not disadvantaging some people, we already know that anonymization is not perfect. Also, all of the care staff around you, all of the people who get your referrals, like you give them non-anonymized data, medical data about yourself. So we already have a chain of trust and custody with our health data that we extend to many members of the medical community and our own maybe personal care community, people who are trusted health advisors or family members helping us. I don't think that we need to have differentially private health models now in many health settings. The question is, what do we do when private companies want to work in health? Because they also often have other data about us, and the goal is to sell us something or provide us with a charged service. And that I think I as a person and also my community in general tends to be much more uncomfortable with, and probably we should be uncomfortable with, right? So I, in my mind, draw a distinction between using anonymized health data, which is not private, it's not secure, right? But there are legal teeth around it with data usage agreements. I'm using it to develop some sort of risk score that's going to be deployed in a health setting where the people seeing the results are healthcare people anyway, who have access to non-anonymized version of your data, versus a fully public posted on a website release of data or selling of data to a private company that might have other kinds of data about you anyway and use it to target you. So I draw a distinction there.
Great. Okay, so it looks like we have 2 questions in the Q&A. So the first one we have is from Ilya Shipster. Do you want to come off mute and ask your question, or I can just read out the Q&A? And let me give you a moment. Okay, let me just read it out. The question is, so the question says, in dimension reduction, there's this idea of sufficient dimension reduction, where instead of doing something like PCA, you instead try to find some subspace in a way that preserves some object you care about, like a regression function. Is there some sort of similar sufficient differential privacy idea whereby you get privacy guarantees while preserving some of the object you want? Or is it fundamentally impossible? Yeah, so that's the gist of the question.
It's not fundamentally impossible to preserve some parts, right? So of data identity or a data facet, right? I think the issue is in this very specific setting, the thing that makes you different is by definition a thing that we need to be aware of often when we're making, so with no differential privacy already, forget about differential privacy, health models have different performances. So that's the sort of pre-existing issue, that it's already there. And now we're in a differential privacy setting where minorities and minoritized populations are very rare. And so we are, disproportionately influencing them, right? Noising and clipping their data. If we were in a setting where all healthcare was practiced completely equally amongst all people, that wouldn't matter. Would it matter that, I'm relying on some other part of the support space in order to make a prediction about you? Probably not. That wouldn't reduce the performance as much. We're just not in that setting, right? And so that's why there's this fundamental trade-off. And I think we also need to define what axes is it okay for us to reduce, right? And so sometimes when you do audits of performance, right, you do it along aggregated audit axes, right? So am I doing well on women? Am I doing well on Native American patients? You pick sort of very specific things. But as we found in this chest X-ray study, it's often intersectional groups that maybe your model is doing worse on. And that could be because it's picking up on cascading bias in the data itself, but it could also be that those cases are harder because of socio-technical reasons, because I have less access to care. So by the time I get to the doctor, my condition looks different than most of the other patients. It could be because I have different kinds of insurance. And so the kinds of treatments that you give me are different than the treatments that you give to other patients. And so I think it's not maybe bad all on its own as an objective statement. It's not a bad thing in my mind if you say that adding more privacy could flip more of the patients in the support training to be of a different ethnicity than this test patient. I think it's problematic in the socio-technical system that healthcare is, right? It's not a bad, so there's a paper that I put up with several co-authors, mostly radiologists, a month ago, showing that you can, with incredibly high fidelity, predict the self-reported race of a patient based on their chest X-ray. And this is true even when you take out a lot of the clinically relevant information from the chest X-ray. So you can blur it, bandpass filter it until it looks really degraded, like to a point where I can't really tell it's a chest, and neither can the 10 radiologists who looked at it. But you can still, the model can still tell, like this is a person who self-reported that they were Black. On its own, that's not bad. It's not bad all by itself as an objective statement of fact that a model could determine your self-reported race from a chest X-ray that's highly degraded. It's bad in a socio-technical system where somebody could create a model on purpose or by accident that performs worse for Black patients, and radiologists who often don't see the patient. They're just seeing a chest X-ray. They don't know if the patient is white or Black. Could be given advice, perhaps, that is always wrong for Black patients. And they wouldn't ever know because they can't extract race. A human expert can't extract this same information from the chest X-ray, but the model can do it perfectly. And so sometimes I think we have to pull out what is the technical thing that we're saying, which on its own, no judgment, is a thing. Think for a second about how these systems are used and then say, but that is probably going to be a problem when it gets used. And so I think that's the difference.
Yeah, and that's a really great point. Thank you for that. And Joe, I see that you had a question that was sort of also related. Do you want to come off mute and ask your question, Joe? We have just 3 more minutes.
Yeah, I realize the time is a bit short now, so maybe there are other questions as well you want to take. But I was just curious about your thoughts on, and maybe you mentioned this in passing, but on different kinds of discussions ongoing now about federated learning models and whether there are problems with that still, or I know that was sort of.
I have very strong thoughts about. So I will tell you, there's nothing wrong with federated learning as a construct, right? So it's a very interesting technical idea. That's not going to solve any problems. And it's not going to solve any problems for 2 reasons. Federated learning works well when I have a known data distribution. I know what the variables are going to be named on my side and on your side. They're similar data. And if I run a model here, it's meaningful that I run it exactly the same way in your place. I don't know a hospital where you could do that year to year. The variables change names. The doctors are different. The x-rays get moved, right? Like I can't think of a single example where federated learning makes sense in healthcare because nothing is that clean. Like if we have beautiful sensors that we've deployed in the ocean and you have yours in your part of the ocean, I have mine in my part of the ocean, and they're all exactly the same. Sure, federated learning works. We're not in that setting here. And I haven't written a paper about this yet, but federated learning is often proposed to me when people don't want to share data and it doesn't address the underlying concern of they want the IP. I want the intellectual property that is my data, my hospital collected on my patients. So federated learning doesn't solve that because there's still this issue of, okay, well, when I throw my model over the fence at you and you run it on your data, and maybe get something incorrect or faulty because our data isn't perfectly mapped. And then you throw it back to me. Who owns that result? Who gets to talk about it? Who gets to release it? And so it's a very cool, interesting technical idea and area. I don't think it fixes anything in health.
Great. Well, thank you. So on that note, we unfortunately have to wrap it up. We're right on time at 1 o'clock. Marzyeh, thank you so much for this wonderful talk. And if anyone has questions, you can follow up with Marzyeh. Her information is online. And thank you again, Marzyeh, and all the audience members.
Thanks, Khadija. Thanks.
Thank you, everyone.